because if you have understood nuclei well, then definitely you can answer the question from nuclei, because the questions that come from nuclei are very limited. I have told this to you in the previous class also. Give me a second. Knock the door. Revan sir, or on the recording, I offed it. Recording is off, on it. Yes, please. Coming back. So, in the previous class, on only. I offed it. Did you on it? Oh, then fine. No issue. Thank you. So, coming back. So, in the previous class, we have learnt nuclei chapter, and nuclei chapter is a part of modern physics, where I said the questions are very limited. From where the question comes from there, if your luck is good, the question comes from isotopes, isotones, isobars, or the question comes from nuclear force, where they will ask you what is nuclear force, and some basic theory questions from there. And the most important part from that chapter was binding energy. I said you what is binding energy? It was the energy which the nucleus is short of to once again become independent protons and neutrons, isn't it? So, nuclei, it is formed because of binding energy only. Since it has less energy than what it needs to become independent, it is formed. So, how much energy it is less, that energy is only known as binding energy. So, more the number, it needs that much energy to be given out from itself to become independent, isn't it? So, binding energy per nucleon versus mass number graph, which you saw, the graph where we had that parabolic curve above and become straight line almost, where we came to know that all the elements which have mass number between 0 to 30 are having less stability, more than 170 have less stability, between 30 to 170 have the great stability, more than 8 almost, isn't it? And the element which has the maximum binding energy per nucleon is iron 56, and if you see this side, uranium has lesser binding energy. If you this side, all the deuterium, tritium, helium, they have low binding energy. So, when you are converting a high BEN, sorry, ulta I am saying, low BEN to high BEN, you have an energy release, that is called as binding energy release. And if you remember what is the meaning of binding energy? Binding energy is ZMP plus A minus Z into Mn minus M of nucleus, isn't it? Do this calculation and multiply with 931.5, you get this much MeV of energy. And if you divide that energy by mass number, then you get binding energy per nucleon. If you are getting your answer more than 8.55, 8.65, your answer is wrong. If you are getting binding energy value as 10, 12, 20, 25, 30, 40, it is wrong, because the maximum binding energy itself is 8.65 only. So, you cannot get the answer more than 9, whatever. I hope you are getting my point. So, binding energy per nucleon numericals can come, where they will give you mass of proton, they will give you mass of neutron, they will give you observed mass of the element, like nitrogen if they say. Then you know what is the number of protons in neutrons and protons in nitrogen. By that you can find the value of ZMP and plus A minus Z into Mn, and then multiply that whole thing with subtract from M of the nucleus, you get binding energy, and multiply with 931.5, you get binding energy in terms of MeV, and then divide by mass number, you get binding energy per nucleon, isn't it? So, the fission and the fusion process also, Jayesh, your video is off. Fission and the fusion process also is purely based upon the binding energy release. I said you, if a heavy nuclei like uranium breaks into two mid-sized nuclei, there are three possibilities of that. So, any possibility if it comes, then there is a conversion of low BEN to high BEN, and whenever there is a conversion of low BEN to high BEN, there will be an energy release. One way is fission. Second way is fusion, and fusion is a process where two low BEN nuclei fuse together to become a high BEN nuclei. For example, that day we talked about deuterium, hydrogen actually. If two hydrogen atoms are combining to become a helium atom, or maybe protium to tritium also, you may get energy release, that is called as binding energy release in nuclear fusion. Obviously, I said that to you, fusion is a better process in terms of clean energy, in terms of more energy. But the problem is, it is very difficult to overcome proton repulsion barrier. If you are able to overcome proton repulsion barrier, only then you can do fusion. That's the reason still today fusion process is very difficult to achieve. We know fusion is good, it is clean, but why it is difficult to achieve is because of the proton-proton repulsion barrier. Jay Aditya, video should be on. Next is, the problem in fusion is the reaction takes place with the help of hydrogen. Hydrogen is abundantly available around us. If a reaction takes place and it becomes uncontrolled, then you can imagine the extent of damage it can cause. If it is uranium, uranium is only what you are giving to it. But if it is hydrogen, it can get hydrogen from the environment also, and that can be a tremendous chain reaction where you will have a huge binding energy release, destructing, a lot. I said you, 5-6 nuclear bombs dropped on the earth, earth itself will shatter. That much power is there in nuclear bomb. So we talked about all these things in the previous class. We solved some numericals also on that day, and I told you how the numericals have to be solved. That's all about the chapter, very simple chapter. What you should remember is binding energy curve, fission, fusion, and remember the reactions. That is fission reactions and fusion reactions. Remember, because sometimes the question comes like, write the reactions happening inside the sun, write the reactions happening for the fission. Like that, remember the reaction, that when there is a unstable uranium hit by a neutron, it becomes uranium-236, and then all the breaking that is happening. So all these things we studied in nuclei chapter. I have told you, these part of physics is easy scoring part. Before last class, some people had some problem in nuclei. I hope now nobody feels that nuclei is a tough chapter. If you still feel, then you have not listened to the class properly, and for that kind of scenario, I have sent the link in the group. You can always see the video and re-listen to it if you want to. If still you feel nuclei is tough, believe me, in whole physics, easiest chapter starts from wave optics, if you understand it. Wave optics, dual nature, atoms, nuclei, semiconductor. It is like making you to pass. Really, there are, if a student joins me and he is not passing in physics, that kind of bad situation student is there, then I will say them, just read volume 2 from wave optics to semiconductor. In volume 1, EMI, AC, electromagnetic wave. That's all. With this much chapter itself he goes, he will definitely get 40 out of 70. So this part of the physics is scoring part. I don't think anybody is there in the class who just wants to pass now. Everybody is in a situation to get good marks. In 70, you can aim for even 70. So if that is the aim, then also these chapters are important because you can easily score marks in that, and you have to spend less time to study. Imagine preparation of ray optics and preparation of nuclei. Nuclei will take 2 hours to prepare. Ray optics will take 2 days to prepare if you prepare day and night. Really, ray optics is lengthy. It's a huge chapter. So don't think small chapter I'll do at last. Small chapters will be strong in that. Don't miss marks in that at least. Fine. Now we have come to the last chapter of physics officially, which is semiconductor. Again, an easy chapter, interesting chapter, simple chapter, scoring chapter. 6 marks in the board examination. Imagine. 7. Oh, your school told 7. Then 7. Now, what is the problem in that? Your school is Kendriya Vidyalaya. You should respect the school. Isn't it? You are KV, no? Yes, 7 they told, and 7 will come. So 7 marks from semiconductor. Imagine 4-5 page chapter, 4-5 page theory chapter, 4-5 page theory chapter giving you 7 marks. Jackpot. Nothing else you need. Now you should not miss 7 marks. Today, by the end of the class, I will even tell you which 7 marks are going to come, from where the questions are going to come. See, we cannot predict questions from electrostatics, current, but we can predict questions from semiconductors, nuclei, atom. Small, simple chapter. Everything you can learn, nothing you should leave. So, don't miss the 7 marks from semiconductor. Fine. Today, if everything goes fine, if you cooperate, don't start feeling sleepy in the middle, then we will be able to complete the syllabus, because I have got a feedback from other teachers that don't keep class till 9:15. Children feel very tired by the class ends. I said maybe, I don't know. Being teacher, we are teaching from 3 hours, we are not getting tired. If you are getting tired, then there is no excuse. So I am not going to stop my class at 9 o'clock, though I have told everybody to stop at 9 o'clock. I will continue till 9:20 only. But if you feel sleepy, you ask me, I will give a 5 minutes of break. Even online people, you can off your camera and go and have your small sandwich or something. But don't do that. Ask me to stop, I will take a break, okay? If you want me to take a break. I hope Jay Aditya is listening to me, and if he is listening to me, then his video is off. I don't know why. Coming back. Yes, yes. Make it fine soon. So today's class, what? Water? I told you to get the water and come, man. After coming here, I will not allow you to come next class. Nirmal, don't do anything which is disturbing me. It's a hybrid class where I am dealing with both the peoples. There people are not on in the camera, I am dealing with them also. Here, if you create problem for me, it will be big issue. Okay, coming back. So, in this chapter, we are going to learn about semiconductors, first I will give introduction about that, it's what it is made up of, how it is found and how it is useful for our use. Next I will talk about the types of semiconductor, intrinsic type which is P and N. Then I will talk about extrinsic type. Actually P and N is the extrinsic only. First I will talk about intrinsic, then I will talk about extrinsic, that is P and N type semiconductor. Then I will talk about the diode which is formed by combining P and N junctions, P and N diodes, and then finally we will talk about the applications of P-N junction diode. That's all. Only one application is there in your syllabus, rectifier, nothing else. Earlier we used to have solar cells and diodes, LEDs and all these things. Now they have removed everything. Only one topic is there, rectifier, half wave and full wave. So let us start the class, and first of all I want to ask you people that where have you seen the semiconductor being used? Have you ever seen semiconductor? Have you ever seen semiconductor? Computer. You opened computer and saw semiconductor. Who is that? Yeah, Balan, very good. How you opened the laptop? Intentionally or I mean by mistakenly? Intentionally. I mean used a laptop, a broken laptop or a good laptop? Using laptop. Why you opened, man? For simply adding some RAM in that. Then? And when decides to open the laptop itself, very good. And what you saw inside? Some semiconductor device you saw. How you know it is semiconductor only? Oh, you searched in Google also, that much you did. Oh my God, good, curiosity is good invention. Okay, coming back. So yes, he says correct. Laptop is all of semiconductors only inside. Electronics, this whole branch electronics has come from semiconductors only. Remember that. If you go 40 years back, no, in engineering today we have electronics and communication engineering, right? One branch is there, which Sari sir also has studied. That branch came 30 years back. Before that, if you go to engineering, there are only 3 branches. I mean, I am talking about 40, 50 years back. Civil, mechanical, electrical, that's all, that is only engineering. Civil engineering, the oldest branch, which I have studied. Next is mechanical engineering, yeah, after civil it came, and then electrical engineering, when people started talking about electricity. That's all was there. But today we have data, AI, machine learning, cryptocurrency, all these things. But the main branches were still that's why it's called as core branches. Have you heard this name? Core branch. Core means civil, mechanical, electrical. Last 35, 40 years, this electronics branch has also emerged, where you learn mainly about semiconductors. Okay. Now semiconductor, when I say, semiconductor can be called in 2 different ways, naturally occurring semiconductors and artificially made semiconductors. Before I go into that is elemental type and compound type, I want to talk to you about like electronics. The term electronics is derived from what? Obviously electron. So the flow of electron is regulated and used through various techniques to run our electronic gadgets, I told you. Now it's not like electrons are there only in semiconductors, it is there in conductors also, isn't it? If you see conductors, they have the most number of conducting electrons. But then why we shifted to semiconductors? Why we wanted semiconductors? Problem is, if it is a conductor, it cannot be made insulator, isn't it? It remains only conductor. If it is an insulator, it will always remain insulator. It cannot be made as a conductor. But semiconductor, you have a control over it. You want it to use as a semiconductor, a conductor, use as a conductor. You want to use it as a insulator, as an insulator you can use. So you can control the conductivity of the semiconductor. See, the world is all about controlling. I have told you, when we found magnets, naturally occurring magnets, we were not satisfied with that. We found in the Magnesia Island, shepherds went, whatever, shoes or stick, something they found that magnets are there in the earth. They took out, used it also. We got naturally occurring magnets, but the desire of human beings to control the magnetic field led to the invention of electromagnets. Electromagnet, how they are better than the magnets? Because we can control magnetic field in electromagnets. Same way, if you have a conductor, it always remains a conductor. If you have insulator, it always remains as a insulator. But if you can control the conductivity and resistivity of a material, it is possible only in what? Only in semiconductor. So, I mean, this is very basic thing. I have just where we are using the semiconductors, you can see everywhere what you are using nowadays, what you are using, mobile phone, laptop, TV, all these things have inside what? Semiconductors only, filled with semiconductors only. So I said, see, base material for almost every electronic component is what? Semiconductor. Now these things what you would have seen Mr. balan inside the system, isn't it? So some of them are transistors, diodes, LEDs, isn't it? This is LED, which we will play in home. Have you tried directly connecting LED to the point? It will blast. Don't try that also. So these LEDs are there, transistors are there. Now different 8-leg transistors, 16-leg transistors are there. I will not go in that detail about these things. But these things were once upon a time there in your syllabus. BJT, transistors were there in the syllabus. Now they've removed everything, made it simple. Get marks, pass, be happy. So these are some kind of, see, these are capacitors. You studied, no? Cylindrical capacitors, those. And there are some small components which are called as semiconductors, and you're going to learn about that. So I said you semiconductors are of basically two types. One is elemental, one is compound. So in nature itself, we have some elements whose conductivity lies between conductor and insulator. Naturally, if you see silicon and germanium, only these two elements. See, I will not say that all the elements having 4 valence shell are semiconductor. Even carbon is like that. But is carbon a semiconductor? No. You may have a doubt then. Why is silicon germanium only? Why this partiality? I will tell you the reason for that also. Because for any element to be called as a semiconductor, there are two requirements. One requirement is 4 valence electrons, that all the group 14 element, what is this, group 14 or group what? 14 element only. I am very weak in chemistry. Group 14, okay. So group 14 elements, all the elements will have 4 valence electron. That does not mean that all the elements belonging to group 14 are semiconductors, no. Because second criteria is there. Second criteria is that the energy gap between the valence band and conduction band should be less than 3 electron volts. Now, that is a very big term. Those who are not knowing semiconductor, what is a valence band, what is conduction band, what is energy gap, all these new terms we will be discussing in today's class. Okay? But remember that two criteria. One is 4 valence electrons, second is 3 electron volt, less than 3 electron volt as the energy gap. If these two are satisfied, only then an element can be called as a semiconductor. Who satisfied that? They satisfied that. Who? Mr. Silicon and germanium. They both were having these both criteria fulfilling. So they are called as elemental semiconductor. Then we made, by mixing different elements, doping and all these things, we started making compound. Like all these things that you are reading here are compound semiconductors. Compound semiconductors can be even thought of like alloys. Like we have metals, we have alloys. So what are alloys? Alloys will increase the efficiency of the metals, isn't it? Why we went for alloys? We want to have more use of metals. You have brass, I mean bronze if you take, copper you have. But we wanted something which is beyond that. So we went for brass, or we went for bronze, or we went for many other, nickel. Nickel is an element, but nichrome. Nichrome is an element. It is a alloy. Like that, various alloys we go in order to make elements more useful. For example, same way you can imagine that compound semiconductors are having more efficiency as compared to elemental semiconductors. In our syllabus, we have to study only about elemental semiconductors. There is no talk about compound semiconductors. I am just telling it for your knowledge. Then let us go into the class. Now the class main part starts, where I am going to classify the solids, which you already know that solids are classified in 3 categories. What are those categories? Metals, insulators, or I should say conductors, insulators and semiconductors. They have mentioned as metals, but actually it should be written as conductors, insulators and semiconductor. I told you it is all about the conductivity or resistivity which decides whether it is a conductor, insulator or semiconductor. For example, if I talk about the conductors, they can conduct electricity and heat mainly. So they possess what? They possess very high conductivity or very low resistivity. Both are same only, reciprocal of each other. So the values of conductivity and resistivity also I have mentioned here. You can note these things down. You can write what is the value of resistivity. And if you remember one thing, second thing automatically you remember, because it will, 1 by this will become 10 to the power plus 2, 10 to the power plus 8, isn't it? Conductivity will be 10 to the power 2 and 10 to the power 8 Simon meters. So this is the conductivity and resistivity of the conductors. I hope you are getting my point. So they have very low resistivity and very high conductivity, both are basically same only. Then comes, shall I give time for writing? Fast. I hope Praneep, Dharan and Amruta are knowing that we are knowing that you are not on in the camera. Mr. Praneep from Sriniketan, camera has to be on, man, don't forget that. Today's last online class for Praneep Dharan. I'll make you to sit down, but I'll not allow you to come at online. Yes, we like this, man. Why are you offing the video here and there, Praneep Dharan?
Sir, no, sir, I want to take my headphones on.
Okay, now you took headphone. Now don't go for taking anything else. Be in the class, okay? Okay. Next is insulators. So, example was copper, silver. Don't ask what is the example of metal. You know very well. Aluminium also you can write. Okay. Insulators. What are insulators? Which are having low conductivity or high resistivity, obviously. So, their values are lying very high. You see 10 to the power 11, 10 to the power 19, very high resistivity. What will be conductivity then? Minus 11 and minus 19, 10 to the power minus 11 to minus 19 Simon per meter. So, these are the values of conductivity and resistivity of insulators, and obviously example can be glass, air, rubber and all these things, wood, mica, they are insulators. So, insulators are the materials that are very poor conductors of electricity. I am not saying they will not conduct, they have written here cannot, but actually the reality is it will conduct very less, negligible. That is why they have used the word cannot, but in reality it has very less conductivity or very high resistivity. I hope you noted down the values. Third comes what? Third comes semiconductors. And what will semiconductors have? Electrical resistivity or conductivity in between metals and insulators, isn't it? So, they will have the value of their conductivity and resistivity in the middle of these two. So, the value is from 10 to the power minus 5, 10 to the power 6 resistivity. So, it will become 10 to the power 5, 10 to the power minus 6. Obviously, conductivity is reciprocal of resistivity. And examples I already told you, silicon and germanium. So, I hope you are clear in what is the meaning of a conductor, an insulator and a semiconductor. It is all the game of resistivity and conductivity. High resistivity, insulator. Low resistivity, conductor. Medium resistivity is semiconductor, between conductor and insulator, isn't it? Don't worry, questions will not come from here. So, I will go to the next slide, shall I? Right, even though it will not come, satisfy yourself, write it. Let me know when you are done. I hope everybody is writing. The way Praneep Dharan is staring at the mobile phone, I think he is not writing. Okay. Please guys, take the notes properly. Shall I proceed? I hope I can. Thank you for allowing me. So, now comes the most important part of this topic, not the chapter, this topic. You should understand the meaning of valence band, conduction band. Many of you or most of you would have learned in the school by now this chapter. I don't know how much you have understood this theory of valence band and conduction band. Today I will try to make it clear for you. I will try from my side. So, even if you are feeling sleepy, put your spit in your eyes and be awake, and please listen to what I am saying. Be very alert. Okay. So, we are talking about energy bands. So, if I talk about the last chapter, I mean I am talking about atoms chapter, not nuclear, atoms chapter. I have told you that every shell or every orbit has a fixed amount of energy, right? When you learned about frequency condition, quantization condition, I told you that a particular orbit will have a particular energy level. Electron jumps down, jumps up. If it wants to radiate some energy, it will come down. Absorbs energy, jump up. But every level, when I say level, I should say the shell has a different energy. That is what is mentioned in the first line here, that a single isolated atom, electrons in each orbit have a different energy linked with it. I hope you know this and understand this line, that every orbit has a fixed amount of energy in a single atom. That chapter name is atom, not atoms, right? They have talked only about one atom. But the problem is, in elemental form, in material form, you never see one atom. You see trillions of atoms, millions and trillions of atoms, am I right? So when the atom comes close to each other, what happens you see? So if I have taken an example of sodium. So sodium is a perfect example of a metal, isn't it? And its configuration, I hope you are able to see. It is 1s2, 2s2, 2p6, 3s1. Most of you know this, which is 11. 11 is the atomic number, if I am right. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium. 11. So 2, 8, 1 in terms of K11. In terms of SPDF, it is 1s2, 2s2, 2p6, 3s1. If I draw this energy level diagram of it, then you will realize that in 1s shell there are how many electrons? 2 electrons. In 2s shell there are 2 electrons. In 2p there are 6 electrons. In 3s there is 1 electron, and 3p is vacant. It is empty. Are you getting what I am trying to say? This is the energy level diagram of single sodium atom. What do you want, man? You want to go inside the screen? Leave the layer online. You have come offline, enjoy offline. If you want to be online, you can also join online and see what their friends are doing. Okay? Concentrate here, Mani, please. I am saying this is an important topic. Coming back. So if you see, this representation of energy level I have done only for a single atom. But unfortunately, sodium will never exist as a single atom. It will exist as a material like sodium metal. If it is a sodium metal, then what is going to happen you see? See, if like suppose I am talking about 2 sodium combining. So, if there are 2 sodiums which are placed, 2 sodium atoms placed close, their energy levels will disturb each other. It means that, read the line you will understand, when 2 single or isolated atoms are brought close to each other, then the electrons in the outermost orbit of one atom experiences an attractive force from the nucleus of the other atom. You know that nucleus is positively charged. Now, suppose if you take the case of sodium, where we had 1s2, 2s2, 2p6, 3s1. 3s1 is the outermost electron, am I right? One electron in the 3s orbital, whatever you want to say. Now, this electron will get severely affected by the nearby atom's nucleus. I hope you are understanding what I am trying to say. So, its energy level will not remain as it was there before, it will distract. That is what it is written here, that when 2 single atoms are brought close to each other, then the electrons in the outermost orbit of an atom experience an attractive force from the nearest atom's nucleus, and due to this, the energies of the electron will not be in the same level. So, now what will happen? The energy of the particular level gets disturbed. The energy level of electrons are changed to a value which is different from that of the original energy level of the electron. I hope you are getting what I am trying to tell. In a single sodium element, single atom of sodium, what is the energy level of each, what do you say, the orbital, and if you compare as a sodium element where we have many atoms, then the energy level will not remain same, especially the outermost energy level, outermost orbit's energy level, it will change. If I just draw diagrammatic form, you will understand that this energy level, I have drawn blue color line, right? Blue color is the energy level of the second atom. So, this 1s green, 1s blue, you can see there is a difference in the energy levels. Are you able to feel? Again 2s, 2s star, 2p, 2p star, 3s, 3s star, 3p, 3p star. So, you can say that this difference in the energy level is happening just because of 2 atoms of sodium. If we have many atoms of sodium, then what will happen, you know, all these energy levels will overlap each other and they will form energy bands, because if I take only 1 sodium, it will have 1 energy level. If I take 2 sodium, it will have 2 energy level. If I am having thousands of sodium, it will have 1000 different levels. Some may overlap, some may not. That is why we make band. When I say valence shell is for single atom. When I say valence band is for many atoms of the same material. Are you getting my point? So, all the valence electrons will lie in valence band, because each valence shell will have some valence electron. If I have thousands of valence shells, it will combine to form a valence band. Are you getting my point? So, what is the meaning of valence band? You are clear in this, or conduction band? Band itself, energy band is what? Energy band is the what do you say, the combination of all the energy levels of a particular orbital gives an energy band. So, it is different for, I mean, I should say, the valence band, and there is something called as conduction band. I will talk about that first. So, if you see, yes, this diagram, you will realize that 1s I have written, 2n I have, what is the meaning of 2n? It will have 2 into n times. If you have 1 lakh atoms, then all 1 lakh atoms will be in the multiples of 2 only, no? Because 1s can occupy only 2 electrons. So, if you have 1 lakh atoms, you will have 2 lakh electrons in 1s shell. Do you understand my point? Here also 2n, here 6n, here 2n, here 6n. That is a maximum they have written. But in reality, how much will be there in sodium? Here it will be 2, 2, 6, 1. Imagine we have 1 lakh atoms of sodium, 1 lakh, 2 lakh, 6 lakh, 1 lakh. Are you understanding the distribution of electrons? Understand this, if you have 1 lakh atom of sodium, 1 lakh atom of sodium will have 1 lakh electrons in 1s, or sorry, 2 lakh electrons in 1s orbital, 2 lakh electrons in 2s orbital, 6 lakh electrons in 2p orbital, 1 lakh electron in 3s orbital. All these 1 lakh electrons are actually in this band, which is a valence shell band, which will be called as valence band. Okay? So, if I define what is valence band, now write this properly. Earlier things also you can leave. I will share the PPT with you if you want, I will share the video with you if you want. Write this definitions mainly, but don't miss this. Energy band which includes the energy levels of the valence electron is called as valence band. Please note it down. All of you who have joined online, please write it down. Energy band which includes the energy levels of all the valence electrons is called valence band. I hope it is clear. I hope you have written this very basic simple line. So, can I say that this is a valence band? In sodium, hey, this is only for sodium, okay, don't confuse, in different elements will have different. Sodium, this will be valence band. Now, next highest band from the valence band, empty or partially filled, will be called as the conduction band. So, what will be conduction band here? 3p will become conduction band. So, what is the meaning of conduction band? It is the next band which is present in like next energy level than the valence band. So, valence band is the band which is next, that is conduction band is the band which is next higher level than the valence band. Are you getting my point?
If it is partially filled, then how will it be called?
How will it be called?
It is partially filled with electrons, then that is called the valence.
There are some scenarios. I am not talking only about semiconductors, I am talking about all the solids, where you would have seen in some cases where the valence electrons may lie, like for example, if you go to 4s, 4d, 5s, like that, if you go, you may see that a particular shell, a particular orbital, there the valence electron will lie, and some electron will lie in the next level also. But don't think that we have to the conduction band will lie above that, it will lie in the same band. I will talk about this in detail if you want further also. But now, as of now, you understand that wherever the valence band is there, above the valence band we will have the conduction band. Okay? If this word partially is confusing you, we will talk about that. Yes, please tell me.
I have a doubt, sir. It is written empty or partially filled.
Same thing she is asking.
Can't the conductance band be fully filled, sir?
Can
Can the conductance band be fully
conduction band, yes. Can conduction band be fully filled, you are asking?
filled? Yes.
No, it cannot be fully filled. It will be always partially filled only because if all the electrons go from the valence band to conduction band, then also conduction band will have some space remaining for occupying some more electrons. Because if you see, in this case you see, example I am saying, 3s is what? Valence band, 3p is what? Conduction band. The capacity of 3s is how much? 2n. What is the capacity of 3p? 6n. If all the electrons of valence shell goes to conduction band also, it will have space for making other electrons to come. That is why I have used the word empty or partially filled. So, partially filled mainly is after the electron starts going from the valence band to the conduction band. It will never be fully filled. Are you getting my point?
Yes, sir.
Coming back to the next thing. One more important thing you would have seen in the previous slide itself, that there is a gap between the valence band and the conduction band. You are able to see this gap? This gap is called as energy gap, right? So, if you see what is energy gap, it is the gap between the top of the valence band and the bottom of the conduction band. Please make a note of it. The gap between the top of valence band and the bottom of conduction band is known as energy gap. It is an important term because the whole semiconductor concept is based upon this energy gap only. Gap between the top of valence band and the bottom of conduction band is called as energy band gap. Some books will also write forbidden energy gap. In some books, you would also see the word forbidden energy gap. Forbidden energy gap is that gap between the valence band and the conduction band. Some books will use the word forbidden because there is no electron lying in that gap. I hope you have copied this. Yes? So, in this case, if you see, energy gap is between the valence band and the conduction band. Mainly the top of the valence band and the bottom of the conduction band. Remember that. It is not like from here to here you can say, or from mid you can say. What is the ending of valence band? What is the starting of conduction band? Between them, what is the gap? That gap is called as energy gap. So, if an electron is somewhere lying in the valence band, imagine there is an electron which is lying in this valence band, and this electron, how much energy you want to supply to make it to go to conduction band? Is this energy only, isn't it? Energy gap. So, we can also say that energy gap is the energy required by the electrons lying in valence band to make it go into conduction band. Are you getting my point? How much energy you need to make the electrons to jump from valence band to conduction band is also called as, or can also be called as, the energy gap. Loudly? Yeah, you can say ionization also. So, this is the energy required to make the electron to move from valence band to conduction band. Is it clear to you? Shall I proceed further? Okay. So, one thing, energy gap is very large for insulators. Common sense. Energy gap will be very small or almost zero for conductors, and energy gap will lie between that two things in the case of semiconductors. We will talk about that next. So, energy gap can be any value, a big value, a small value, or even zero. So, if you talk about the energy band diagram for metals. So, metals, there are two possibilities. See here, it will make it little clear to you. So, if you see, I have drawn two bands here. One is valence band, one is conduction band. So, in this case, you can see very clearly where is the energy gap lying, isn't it? What is the energy gap? This is energy gap. There are some conductors which have a very low value of energy gap. Energy gap will be very, very low. Usually, most of the conductors or most of the metals, their energy gap is zero. I will come to the next slide, you will see that. So, I am saying here conduction band is partially filled and valence band is partially filled. This is one condition. Second condition is there, we will talk about that condition, where you will see that these both bands will be overlapping. Mainly conductors, the conduction band and the valence band overlaps each other. So, whatever electrons are there in valence band can easily move to conduction band. Understand one thing, if the electron, see many children will have this confusion, free electron and valence electron are the same. No, valence electron will become free or will become conduction only if it is reaching in conduction band. Are you getting my point? Almost all the elements except the elements which are having the full shell, that is called as halo, what do you call it? It is that last thing, that neon, argon, xenon, krypton, noble gases. Except that almost all the elements will have partially filled valence shells. Are you getting my point? So, when the valence bands are partially filled and we are talking about what we are talking about? Yes, I was talking about the metals and conductors. Almost all the elements which are metals, there will be, I mean the electrons that is there in valence band, we are talking about, sorry, free electrons and valence electrons. So, valence electrons are the electrons that lie in the valence shell. If you talk in terms of a matter, it can be electrons lying in the valence bands are called as valence electron. But electron, if it is able to move from valence band to conduction band, only then it will become a conducting electron or also called as free electron. Are you getting my point? An electron can be called as a free electron only if it is moving from valence band to a conduction band. First understand this. In metals, you will see generally all the metals are having conductivity, isn't it? Almost all, because their valence band and conduction band are overlapped with each other. But there are some metals, exceptions are there, where this will be there, that is there will be some energy gap, and since energy gap is there, it needs a little push. With a little extra energy, electrons can easily reach to the empty energy levels above the filled ones and a conduction is possible. So, you need to give some energy to make the electrons to move from valence band to conduction band in the previous case. Second is if they are overlapped, like I said, most of the conductors this only will happen. What? Overlapping of conduction band and valence band. Since it is overlapped, electrons can easily move from valence band to conduction band. So, the valence electrons can also be called as free electrons here. Are you getting why? Because valence electrons now are able to move to conduction band easily. In your small class, how you have learnt, you know, you have learnt like if electrons are less than 4, in 9th you learned this, if electrons are less than 4, then what will happen? They will be able to, very carefully, come. You may have to move a bit. Coming back. So, I said that, what I was saying? Yes, in small class, I was talking about small class. So, in small class you have learnt that if a particular element has valence electrons less than 4, it is metal. You remember this? If it is more than 4, it will be non-metal mostly. Why we are saying like that? That time we were talking like 4 is the optimal number, less than 4 it can easily go from the valence shell, and more than 4, that is 5, 6 or 7, it will gain something to become octet satisfied, something like that we studied in 9th standard, structure of atom, isn't it? But now we are talking in terms of shell. So, we are understanding that if it is a metal, then there is an overlapping of conduction band and valence band. Since there is an overlapping of conduction band and valence band, then the electrons present here in the valence band are automatically allowed to go to the conduction band. But in the case of insulators, what I am going to tell you, that is the energy gap will be huge. Huge means the energy gap you see in the case of insulators, it will be more than 3 electron volt. Now, the electron present in this valence band will not be able to go to the conduction band itself. So, from here to here, electron will not be able to go. You may say, how sir, why sir? I am giving energy, why it should not go? I am giving energy, it should go only, no? You give energy, give energy, give energy. What will happen? It will change its state. Take a wood and try to make it conductor by supplying energy. What will happen? It will burn and become ash. Are you getting my point? The material itself will change itself. It will not remain the thing that you were trying to give the energy. That's what happens in insulators. That whatever energy you try to supply to these electrons, even if you try to supply energy more than this value, suppose the energy level is 6 electron volt, energy gap, and you give 7 electron volt, you may say, sir, now I gave more than that energy gap. No, it should go right. Why? Before that happens, it will burn and it will become something else. That is the problem in insulators. Energy gap is too huge that the electrons are not able to travel from valence band to conduction band. And if I talk about the third thing, which is semiconductors, it has the optimum value, that is less than 3 electron volt. Here, if little bit of energy is supplied, then the electrons will be able to move from where to where? From valence band to conduction band. And if it is not there, it will be remaining like an insulator. Are you getting why we have more control over that? In the case of conductor, there was an overlapping of the valence band and conduction band. So whatever electrons are there, they will be always conducting. In the case of insulator, we had a huge energy gap between valence band and conduction band. So whatever electrons were there, they are always what? Not conducting. But if the energy gap is in such a way that much energy supply we can make the electron to move above, then we can have control over it. If we don't supply energy, insulator. Supply energy, conductor. That is what is the control we have over semiconductor, where if you see this, you will realize electron can easily go from its conduction band. And if you see the diagram clearly, you will understand that I have drawn something like this in the grey color, isn't it? Are you able to feel it? There is something in grey, sorry, not this. Yes, I am talking about this and this. They are called as holes. Now, what is the meaning of hole? Hole is a cavity, it is called as positive cavity. It is positive cavity produced because electron is leaving a site. I will explain this to you, please pay attention. Holes can be defined in two ways. One way is electron leaving a site creates a hole. Second way is if there is a condition where there is a requirement of an electron, there also hole will form automatically. I will repeat this. Here we are talking about something else, I am talking about something else. First thing is this, electron is leaving a site. If electron leaves a site, what we get? A hole, positive cavity we get. Second is, electron is there and it wants to make a bond with another electron. Automatically hole will form so that it will attract some other electron to that point. So what is the meaning of hole? Hole can be defined as a positive cavity created by the electron leaving a site. Hole can also be called as deficiency of electron produces a hole in order to make the electrons to get attracted to it. Are you getting what I am trying to tell? If an electron is there, which is what do you say, it wants to make a bond, but if it wants to make a bond, it needs another electron, covalent bond. So for that, automatically the site will create a hole. This hole will attract some other electron and make this electron to get bonded. Are you getting my point? So here if you see, I have talked about semiconductor and I have told that I have even given the values of energy gap of semiconductor. Silicon is 1 electron volt, germanium it is 0.74 electron volt. And if you see in this, one important thing is mentioned. First thing is at absolute 0. So at absolute 0, the electron, no electron has the energy to jump from valence band to conduction band, and it is a pure insulator. But at room temperature, the electrons, some valence electrons gain energy more than the energy gap and move to the conduction band to conduct electricity. Are you getting a point? So this question has come in the board examination. At what temperature the semiconductor behaves like an insulator? What is the answer? Absolute 0. What is the meaning of absolute 0? How much degrees? 0 Kelvin means how much degree Celsius? Minus 273 Kelvin. So if you want a semiconductor to behave as a pure insulator, what temperature should you give to it? Minus 273, very, very, very low. But at room temperature also, it will not be a perfect conductor. Only a few electrons that gets energy to overcome the barrier, that is I should say forbidden energy gap, only they will jump. Some other electrons may still remain here. It wants to get more than that energy to jump above. Are you getting my point? You may ask reason for that. Reason is all the electrons will not be in this position, no. I said you multiple combination of atoms will lead to many energy levels. Now if suppose this is 3s1, 3s1 itself, if it is 3s1, 3s1 will have how many? 2n electrons, I said you. If it is 2n electrons, then you can imagine that all the electrons, suppose here we have 2 lakh electrons, don't think 2 lakh electrons will be only in this position. Some will be here also, some will be here also, some will be here also, isn't it? So the energy required by this electron may be little more than this electron. This value what is mentioned here, no, is the minimum. Energy gap is what? From top of this to bottom of this, isn't it? So if you supply 1.1 electron volt, only this electrons will travel to above. Are you getting my point? If some electron lying here, it needs more than 1.1 electron volt. Lying here, more than that. Lying here, much more than that. Are you getting my point? So don't think that if you supply 1.1 electron volt, all the electrons will jump above. No. Only the electrons which were lying in this top region of the valence band, only they will be able to jump above. If you want all the valence electrons to jump above, still more energy is required. I hope you are getting my point. You may, because by seeing this slide you may get confused. Oh my god, absolute zero is almost impossible. So it means that semiconductor is a conductor only. You may think that room temperature semiconductor should behave like a conductor only. No, because semiconductor at room temperature will not have that great conductivity as conductors, because they conduction band, valence band overlapped. Whatever electron is lying in the valence band, they will be able to easily go to the conduction band, but not in the case of semiconductor. At room temperature also, only a few electrons that were able to get the temperature. See, temperature is energy, I hope you know this. E is equal to 3 by 2 kT, studied in 11th standard. Which chapter you know? Chapter name is kinetic theory of gases. Remember, E is equal to kinetic interpretation of temperature. Temperature becomes energy. How much the value is? 3 by 2 kT, Boltzmann constant of temperature. So whatever temperature you have, that temperature will convert into energy. So that room temperature will create how much energy, or almost this much energy, which will help the electrons to jump from the top of the valence band to the bottom of the conduction band. But there may be some electrons which need more than that energy. That energy can be supplied only if you give energy to it. Are you getting my point? So to semiconductor to behave as a good conductor, you need much more energy than what is supplied by room temperature. I hope you are getting my point. If yes, that is what is mentioned here. At room temperature, some valence electrons gain energy more than the energy gap and move to conduction band to conduct electricity. Is it clear to you? Is it clear to you up to here?
Yes, sir.
So I hope the basic concept is clear of, if you are listening properly, the basic concept of band is clear. In the case of solids, valence band, conduction band overlapped. In the case of insulators, valence band, conduction band, more than 3 electron volt, energy required is very high, electrons will not be able to go to the conduction band. In the case of semiconductors, the energy gap is less than 3 electron volt, like 1.1 for silicon and 0.74 for germanium. So if that energy is provided, it will be able to jump from valence band to conduction band. At absolute zero, it behaves like an insulator, and at room temperature, it has some conductivity. It behaves like a conductor, but not as good conductivity as normal conductors. If you want to increase the conductivity, then what do you have to do? You have to increase the temperature, because temperature will become energy. Energy will increase the, make the electrons to jump from valence band to conduction band. Is it clear up to here? Sure. You want a 2 minutes of break? No. I can give, but what you will do with the break? These people, I don't allow you to go outside.
Yes, sir.
Yes means what? Break you want, man, Jayesh?
Yes, sir.
Okay, I am giving 2 minutes of break, man. Yeah. But you may off your video if you want, but after 2 minutes you can on the video. You should on the video. Jayesh, had your cup of coffee?
No, sir, I just went to fill my water bottle.
Okay. Manojit, Amruta, Tanushree, Samyukta, Yuvanesh, Yuvan, Disha, please be back. I hope you are there, alive.
Yes, sir.
Okay. Shall I continue then? Water, no option. My water. Then? Oh. Ah. Yeah. That much swiping is not allowed. I'm going to make only volume 2 question for today. You want volume 1 paper? That is too difficult for us to correct, man. Don't do that. That much torture don't do. Volume 2 you write, next week you write volume 1. Okay. What, man?
Yes, he wants to sleep.
Feeling cold. Up behind there will be a sweating still. That's the problem. I'll do one thing, but yes, yeah. Tell me, Jayesh.
Will we be having semiconductors, the volume 2 test or?
Yes. You will be having, man. That's why I'm teaching today, no?
Okay, sir.
Okay. How to swim? 50 mark, Tambi. 50 mark and 2 hours. These 2 weeks. From December 1, 70 mark and 3 hours. I hope it is reduced a bit, affects you less. No option. Bear that. Everything I'll tell you. All doubts now only you want to ask. Ask me after the class gets over. They are waiting to start the class. See, eagerly waiting in the online mode. Okay, coming back. So, we are starting, guys. Nikhil, ready? You want some water to put in your eyes? Samrut, Harini? Took one small nap, no, between. Now awake or you want some water? I cannot send you out. I can give my water bottle to put some water on your eyes. Shall we continue? Okay, please. Done, Pavan? Please, focus here now. I said you, when an electron leaves the valence band, it leaves some energy level in the band as unfilled, and that energy which it is leaving unfilled is only called as what? It is called as holes, isn't it? So, these places where there is a cavity forming because of what? Electron leaving the site is known as holes. Unfilled regions are termed as holes in the valence band. They are mathematically taken as positively charged carriers. Remember that, not theoretically or not conceptually. Don't think that it is proton. Many of you think this like a proton. It is just a positive cavity. Its charge is positive, no doubt in that, but it is not proton. But we assume it to be like a positive charge carriers. Okay. So, movement of holes is considered as a positive charge moving from one position to another. Like how a proton moves, we will talk about holes in the same way. But you will understand by today's class that holes movement is virtual, not actual. Holes movement is virtual, not real, not actual, because it's not that a hole is moving. Electron is keep on moving and we feel that hole is moving. We will come to that point. So, now let us enter into the intrinsic semiconductor, main part once again starting now, where we will have questions from this part. What is intrinsic semiconductor, what is N type, what is P type, it is coming extrinsic, but first we will have to talk about intrinsic. Intrinsic means naturally occurring semiconductor. I said no, in the earth itself we will get some kind of semiconductors like silicon and germanium. How are they and what is the formation of them and how it works, we will talk about that. So, intrinsic semiconductor is called as pure semiconductor. Are you getting my point? They are pure, there is no impurity added in that. So, the most widely used semiconductors or widely available semiconductors are two, which are silicon and germanium. Now, silicon, if you can see, it has atomic number as 14 and its shell is, as I mentioned, 1s2, 2s2, 2p6, 3s2, 3p2, and germanium is 32. So, it will also have 4s2 and 4p2. So, as I said to you, at room temperature, the conductivity of intrinsic semiconductor is relatively low because there are very few charge carriers available. Very important point. So, at room temperature, they have conductivity, as I said to you, but not as great as conductors. Reason being, there is relatively low charge carriers. The conductivity is all about charge carriers, isn't it? In conductors, you have a lot of free electrons, so it has very good conductivity. But in semiconductors, you don't have enough free charged carriers because energy gap is there. The electrons are not able to move from valence band to conduction band at room temperature. So, how will you have many charge carriers? If we had 2 lakh electrons in valence band, only 10,000 went to conduction band. Some conductivity is there, but still 1,90,000 electrons are remaining in the valence band only. They will go only if you supply little more temperature. Are you getting my point? I hope you are understanding this. So, that is the problem in intrinsic semiconductor, where the availability of charge carriers is low. Now, let us talk about the structure. I am going to talk about the atomic structure now. Please pay attention. So, I hope you know that this 4 valence electron thinks they will make covalent bonds. Am I right? This carbon also makes covalent bond, catenation property and all these things. So, coming back to silicon germanium. So, if there is a silicon atom which has 4 valence electron, it will combine with other silicon atoms or other germanium atoms to make its covalent bonds. Octet, again 8 things has to be filled. if you see this particular silicon has made a covalent bond with nearby 4 what atoms? Silicon atoms. What is this bond? Covalent bond forming between the nearby silicon atoms. Now, this is how it looks like. I mean, this is one particular silicon. I have represented one silicon with other 4 silicons nearby, and this diagram is the real how a silicon material look like, a crystalline structure of silicon will look like. So, if you see any particular silicon atom, it will have 4 bonds nearby. If you see this 1, 2, 3 and 4 will be there, which are not drawn, maybe in this direction. See here 1, 2, 3 and the 4. Are you getting? So, each silicon atom is having, that is 4 valence electron, and all the valence electrons are bonded with the nearby silicon atom. That is how the structure of silicon is. Now, if you see here, they have taken the example of germanium, the same thing that I have told to you before some time. We are more interested in this thing now. We are more interested in talking about the energy, that is bands. So, valence band and conduction band. Before some time I told you that silicon is having energy gap of 1.1 electron volt and germanium is having 0.74 electron volt. So, germanium having energy gap of 0.74 electron volt. So, as I said, valence band will have many valence shells. So, electrons are lying in the valence shells, okay? And these electrons, when they are getting some energy through temperature mainly, what will happen to them? You see how I have drawn? They will start to, see, I gave some heat energy. The moment I get some heat energy, then one of the electron broke and went outside. If one electron has gone, what it will create? A positive cavity, or called as hole. Further, not only here, some electron may would have gone from some other place also. For example, here broken. Also on the right hand side, I am representing how it is happening. One electron is leaving its side and going to conduction band from valence band. So, these electrons, which electron? Electron which has come here, came here, they are free electrons or called as conduction electrons. Are you getting? Other electrons are valence electrons only, but they are not conduction electron because they are lying in valence band. I hope you are getting my point. They are also valence electron, but they are not conduction electrons because they are lying in which band? Valence band. But these 2 electrons have got the energy by temperature and jumped to conduction band, leaving 2 space for hole also. Now, these holes, what they will do? They will call some electron nearby, because positive cavity attracts negative electron. So, that will make, see, one electron from here jumped and joined this place. Now, this place became filled, but here what came? A whole cavity came. Now, this hole will start attracting some other electron. So, this will jump here. So, hole is not moving, but if you see in the one way, hole came from here to here to here to here to here, it will keep on moving, right? Is hole moving literally? No. Who is moving? Electron is moving, but that makes the hole also to move. As I told, holes will virtually move, electrons will really move. Are you getting? But even then we can say that holes are moving because past positive cavity is moving from one place to another place. So, these electrons you can say from here, valence electrons have represented covalent bonds and the broken covalent bonds. So, how the covalent bonds are broken? By the heat energy supplied externally, and then the electron jumps from where to where? From the valence band to conduction band, becoming conduction or free electrons and creating a space in the valence band for whom? For holes. I hope it is clear to you. Very basic thing of intrinsic semiconductor. So, the thing is, in intrinsic semiconductor, the number of thermally generated electrons are always equal to number of holes. I hope you understand why. If you go diagram, you will realize if there is one electron moving, one hole is produced. 2 electrons moving, 2 holes is produced. 1000 electrons moving, 1000 holes are produced. 1 lakh electron moving, 1 lakh hole is produced. So, always the number of holes and number of electrons is same in what? Intrinsic semiconductor. This question comes in the board exam, that in an intrinsic semiconductor Ne is equal to NH. So, I have mentioned here also. So, if you see in the case of intrinsic semiconductor, if I take Ne is the concentration of electrons and Np or NH, whatever you want to write, as the concentration of holes, then Ne and NH are always going to be same. Nilesh slept sitting on the sofa, off the video, coming back. So, Ne is always equal to NH. So, Ne is equal to NH, I am writing it is also equal to Ni. What is the meaning of Ni? Intrinsic semiconductor, intrinsic ion concentration, both in terms of electron or hole. Ni they are writing it as. So, you can say that the quantity Ni is referred as intrinsic carrier concentration. So, it is equal to Ne, it is equal to NH, you can call it as Ni itself. Are you getting my point? So, if you see here, what I am doing now, you see, I am connecting a potential from outside. This potential is going to create an electric field. Obviously, if there is a potential, what will be there? There will be an electric field, and electric field will make the electrons to move in the direction of electric field. Are you getting? So, when it is moving, there is a production of holes, and once again the holes are calling the electrons to come toward itself, and this process keeps on repeating, and that is how the semiconductors, intrinsic semiconductors are having conductivity. Are you getting how it is getting the conductivity? The moment you have a silicon, it is already having covalent bonds. At room temperature itself, some of the covalent bond gets broke. Why? Because room temperature also will give some energy, 3 by 2 kT. That energy, the covalent bonds will break. When the covalent bonds are breaking, electron leaves the site. If electron leaves the site, hole is produced. Nearby electron will get attracted towards the hole. Electron once again moves, hole is created. Once again, this hole will attract another electron. This process keeps on getting repeated, and there are equal amounts of electrons and hole produced. The current which flows in an intrinsic semiconductor consists of both electron and who is sharpening here. This Pawan guy is making the pages to go and seeing left and right. Small sound also, this is studio, man. If you drop a pin also, it will be heard if there is a floor visible. Please don't disturb. Be here. Coming back. So, current which will flow in a intrinsic semiconductor consists of both electron and hole current, and that is why we are calling the net current in the case of semiconductor as I is equal to IE plus IH. We have talked about this in current chapter itself, you remember. In current chapter itself, conductivity topic, we have talked a little bit about this. So, the net current will be always a summation of IE plus IH. One thing you see, if the protons are moving, the positive charge is moving in this direction, the current will be in the same direction. I hope you remember what is the meaning of conventional current. Conventional current will have the same direction as that of proton movement, positive charge movement, and electron moving in this direction will also create current in this opposite direction, because electronic current is in the opposite direction of movement of electrons. Conventional current is in the same direction of movement of protons or positive charge. Here positive charge is moving this side, negative charge moving that side. So, the net current will be both which direction? Towards left, isn't it? IE and IH both towards left. So, the net current in an intrinsic semiconductor will be the summation of current by electron and current by hole. So, IE plus IH. I have written one point here. At room temperature, conductivity of intrinsic semiconductor is very low. Therefore, no important electronic device can be developed by using this semiconductor. We are learning about theory of it, but are we using it anywhere in devices? No. We are using silicon where? In solar cells. But we are not using silicon directly in any computer. If you open, will not have silicon inside, because silicon or germanium, the conductivity is very, very low. I don't want to supply heat from outside to make it more conducting, right? I cannot sit and supply heat now. That is also energy supplying only, no? For getting energy, why we want to supply energy? It's waste of like energy only after all. So, we go for higher conductivity, which is shown by whom? Extrinsic semiconductor. So, we will go to that topic now. I hope it is clear to you, the concept of intrinsic semiconductor. Application of semiconductor. Solar cells will have silicons or germanium plates, where if there is a temperature falling, heat is falling on that, what will happen? Electrons will get energy and jump from valence band to conduction band. What it will do? It will create current, and that current is stored in the battery. I mean, not current, the potential energy is there, and that energy is stored in the battery, and we will use it later for our purpose. Don't think solar energy directly you are using. By solar cells, we are charging the battery only, and you have that battery charge, it will supply to your home as the current through inverter. It is DC current. Don't think solar cells are AC current. We convert DC into AC by using inverter only, but what we get is DC current, not AC current. And DC current can be stored. AC current has to be immediately supplied. Coming to the next topic, which is extrinsic semiconductor. So extrinsic semiconductors are those where do some kind of doping. Now what is doping? Adding impurity. So why we add impurity? To improve the conductivity of the intrinsic semiconductor. So what we do doping. So what is doping? It is a process of adding impurities deliberately, obviously, not by mistakenly. Some impurities can go by mistakenly, isn't it? Mom is making rice, some poochie can go inside rice without, if they are not seeing properly. That is unintentional doping. But some person, like if you make food for your friend, you will intentionally add some poochie, isn't it? Deliberately you will do. that is only doping. So doping is deliberately done. But mom will not do deliberately. I am 100% sure. I hope that age is not come. You may do for your children. I don't know about that. But our mothers will not do for us, adding doping in our food for what we are eating. So something like doping is deliberately adding some impurity, very small amount of suitable impurity. See, here the word suitable is very important. You may feel simply he has written, but no, the suitable word has its own importance. If I want to sell chili powder, okay, I am businessman, I want to sell chili powder and I want to make huge profit, I want to become Ambani overnight. So I will start adding impurity in that. Now, if I start adding cement in that, in my chili powder, I will be called as foolish only. Because grey color cement, I am adding with red color of chili powder, it will look like some other color. But if I am wise businessman, what I will add? Rangoli. Okay. What? Brick. Yeah, good man, thank you. So we will take one brick, break into powder form, add that and sell. What I chose? I chose a suitable impurity. If I want to sell chili powder with doping, illegal, wrong, ethically wrong, I am not doing it really. In that case, what we will add? Suitable impurity you will add. You try to add unsuitable impurity, that will not do your work. Same thing happens in the semiconductor also. If you want to do doping, doping must be done by suitable impurity. We will talk about this in detail when we go to impurity adding. Okay, coming back. So these impurity atoms are what they are called as? Dopants. Doping is the method and dopants are the impurities. In our case, brick becomes dopant, isn't it? What you are adding as the impurity, that becomes dopant. And why are we doing doping? To increase the conductivity. So it is written as, due to doping the conductivity of semiconductor is increased manifold. You know why? This word you will understand now. How much impactful can be doping? Doping sometimes can be very, very impactful. We will talk about that. So if you see, the semiconductor containing impurity is known as extrinsic or impure semiconductor. So what is intrinsic semiconductor? Pure semiconductor. Nothing doping is there. Extrinsic is impure semiconductor. Why? Doping is done in that. Some mixing is done in that. Now not for any wrong thing, mixing we are doing for increasing the conductivity only. Okay, let us see how it enhances the conductivity. There are two kinds of dopants. One is called as P-type dopants, one is called as N-type dopant. This P and N has come with some reason, positive and negative. We will talk about that. So P means, and N means trivalent. Tetravalent, oh my god, some other valency you are making. No tetravalent here, trivalent and pentavalent only. So N is trivalent and P is pentavalent. Okay, good. Sure, what she is telling is correct. N is pentavalent and that's why I said you, P is not for pentavalent, P is for positive. It is N type only. Okay. So we will talk about that now, but understand that there are two kinds of dopants. One is called as trivalent, which is going to be used. Another one is called as pentavalent impurities. So the pentavalent impurities will be those whose valency are 5. That's why it is called as pentavalent. 5 valency. Examples I have written here: arsenic, antimony. Write these things, very important for the examination. Now we have come to the important part of the chapter. Questions will come from here. What are different dopants used in semiconductor? One is pentavalent dopant, another is trivalent dopant. So what pentavalent will do, you see? So in the case of pentavalent impurity, please pay attention, 2 minutes, I will give time for writing, 2 minutes please. If you are going to add a pentavalent impurity, out of these 5 valence or 5 electrons, valence electrons in this phosphorus, 4 will be used for forming covalent bonds with the nearby silicon or germanium. 1 electron is what? 1 electron is free, empty. This electron will try to create conduction because it is free. You need not to supply energy for it to become free. By default, it is free. I am not going to add 1 atom of phosphorus. I am going to add millions of phosphorus. Millions of phosphorus will create millions of free electron. Are you getting? In addition to what conductivity an intrinsic semiconductor is going to get by temperature, we are going to increase the conductivity because we added millions of pentavalent atoms inside the intrinsic semiconductor. Are you getting? Because all these millions of pentavalent impurities are going to form covalent bonds with the germanium or silicon, and single electron which is left out are going to be used for conductivity. So since it is going to have an electron which is going to be left out, that's why it is becoming negative, and that's why it is called as N-type semiconductor. If you add pentavalent impurities, yes, tell me, man. I will repeat once again. I said that whenever a pentavalent impurity is added in a intrinsic semiconductor, then the 5 valence electrons of this pentavalent impurities, out of 5, 4 valence electrons will form bond. I will show the diagram also to you now. Suppose this 4 electrons are going to form bond with the nearby silicon atom. This 1 electron is free, isn't it, Jayaditya? This 1 free electron will add to the conductivity of the semiconductor. Are you understanding it?
Yes, sir.
So since there is going to be 1 extra electron for each phosphorus atom, if I am going to have 1 lakh phosphorus atom added, I am going to get 1 lakh free electron extra. Am I right, Jayaditya?
Yes, sir.
So we'll have too much of extra negativity because electron is negative in nature. That's why it is called as N-type semiconductor. Here N means negative type, nothing else. I hope you are getting my point. Clear, Jayaditya?
Yes, sir.
Yes. Next type of impurity is what? Trivalent impurity, which has 3 valency. Examples can be boron, indium, aluminium. Remember these examples. Questions are going to come from here. Write 2 examples of pentavalent impurity. Write 3 examples of trivalent impurity. Aluminium, boron, indium. They have 3 valence electrons. If they have 3 valence electrons, how they help? See, common sense. They will have 3. So if their nearby one silicon is there, 3 will get bonded. 4th one is not there to bond. I said in the before some minutes to you that if there is a vacancy of electron, that will also create a hole. Hole is not only created by movement of electron, hole is also created by requirement of an electron. Requirement is there, it will create a hole. For that hole, electron will come and jump. Are you getting my point? That's what happens in the case of trivalent impurity. Trivalent impurity, if you are adding, it is going to create a hole, and that hole is what charged? Positively charged. So I am going to have net positive charge. That's why it is called as P-type semiconductor, which is positive type. So positive type or P-type semiconductor is formed by adding which impurity? Trivalent impurity. And N-type or negative type is added by which impurity? Pentavalent impurity. Many children confuse and forget and they write ulta. P, pentavalent they will write. No. No, it is general, not only her mistake. I have seen many children doing it. So it is ulta actually. If it is p-type semiconductor, it will be more positive, and so it is by trivalent impurity. If it is n-type semiconductor, it will have more negativity, so it will be coming by pentavalent impurity. So pentavalent impurity will form n-type semiconductors. Clear? Sure? Okay. Now let us go to the formation. Okay. So very important thing. The selection of dopant. I said you, dopant has to be selected such that it does not distort the original structure. It occupies only a very few of the original semiconductor atom sites in the crystal. Okay. Now this point is very important. I said you, when you are selecting a dopant, you should not select just because something is chili powder is there. Cement also is very fine like chili powder. So can I add cement? No, because its other characteristics are not matching. So not only the size matters, many other things also should match. That's why it's not like all the elements having 3 valency can be chosen as trivalent impurities. All the elements having 5 valence electrons can be chosen as pentavalent impurities. No. If you see periodic table, you will realize only the elements which are lying nearby silicon and germanium, only they are chosen as the impurities. You know why? Because their size, their characteristics will be similar to that of silicon and germanium. I cannot choose any element which is having 3 valence electrons as a trivalent impurity. I cannot choose any element that has 5 valence electrons as pentavalent impurity. I should choose based upon the size of it. So always it is, if it is just observe that the impurities are always chosen around it. If you see the periodic table, you will realize that the impurities that I have chosen for pentavalent are nearby that silicon and germanium. Even trivalent are nearby. So these are the conditions required for choosing the impurity. Now we will talk in detail about n-type semiconductor. I just told by mouth. Now you will see the diagram what happens. So when you see, when in a particular semiconductor like germanium I have drawn here, it has 4 valence electrons. Am I right? Germanium has 4 valence electrons. In this germanium, if I am going to insert one arsenic, arsenic has 5 valence electrons. If I am going to insert one arsenic, then you can see very clearly what happens. Bond formation takes place, isn't it? And this bond formations takes place in such a way that one electron is extra remaining here. Don't you think so? Extra electron is there, no? This extra electron only is going to increase the conductivity of our germanium. Are you getting? And I said you, I am not going to add one arsenic. I am going to add parts per million. Many things I am going to add, and it is going to create a huge impact on the conductivity of semiconductor. So if you see, the by natural process, I said you, any intrinsic semiconductor, its covalent bond will break, it will create a hole and electron. This is going to happen. Additionally, I am going to get these electrons. So net what do you say, the concentration of which is going to be more, electron or holes? Common sense, electron is going to be more, because I have extra electron per arsenic atom. Each arsenic atom is going to give me one extra electron, and the holes produced will be always equal to the electrons which are produced by leaving the site. So in intrinsic semiconductor, Ni, Ne and NH are same, but if you add doping, extra electrons will be produced. So the concentration of electrons is greater than the concentration of holes. For whom? For n-type semiconductor. We are going to talk about that now. And let us talk about the energy bands also. So if you see the germanium's energy band, energy gap is 0.74 electron volt, and then the electrons, one very important thing, question comes from here also. This level, are you seeing one level is there? This is called as donor energy level. Now what is that? I will tell you about that. All these electrons which were there, valence electrons, are lying in which band? Lying in valence band, right? And these valence band electrons, they are going to where? Conduction band if they are getting the energy greater than equal to 0.74 electron volt. Am I right? These extra electrons are there, no? For each arsenic atom, they are already having conduction, isn't it? So they are lying in a band or in an energy level which is near to conduction band. Are you getting my point? I will repeat what I am trying to say. In germanium, naturally, all the valence electrons will be lying in valence band. If they get an energy which is more than or equal to 0.74 electron volt, they jump to conduction band, right? But when you add an impurity like phosphorus or arsenic, a pentavalent impurity, then all these extra electrons, each arsenic will have a single electron extra. They will not lie in valence band. Why they should lie in valence band? Because they are already free, they are already ready to move, isn't it? So they will lie in which band? Almost a band which is very near to conduction band, very small, see 0.045 electron volt, not even 0.1, 0.05 electron volt almost. This level where the extra electron of the pentavalent impurities lie is called as donor energy level, and donor energy level is always near to the conduction band. Very important thing, it comes in the examination. Donor energy level is the energy level where all the extra electrons produced because of pentavalent impurities are lying, and this energy level is always near to the conduction band. How much near? 0.045 electron volt. So almost matching with the conduction band only. So if you see the diagram I have drawn, this electron requires almost negligible energy to go above. Other electrons, same method, they will go produce hole, go produce hole. Are you getting my point? What is going to happen? Is it clear to you what happened? Yes, please. Can temperature go below 0, man? What is the meaning of 0, you know? Yeah, obviously it will start, if it is going 0 degrees Celsius below, then the temperature will start reducing, energy will reduce, and the breaking of bond will become more difficult. So conductivity of semiconductor will start reducing. If it is going to absolute 0, it will stop, it will become insulator. If it is anything below, above 0 Kelvin, it is going to have some conductivity. Are you getting? It is a game of how many electrons moving. At room temperature, I told you, suppose there are 2 lakh valence electrons, if 10,000 is going above, then maybe room temperature. If I am making 50 degrees Celsius, 50,000 may go above, 100 degree, 1 lakh may go above, 200 degree, all 2 lakh may go above. Are you getting? It is all the game of temperature. I am just giving example, not the real values. Okay. So the same thing I told you now. Whenever an intrinsic semiconductor is added with, these impurities are called as donor impurities. This also is an important term. Donor impurities. What is the meaning of that? The pentavalent impurities are also called as donor impurities because they have extra electron to donate for the conductivity of the semiconductor. That is why these impurities are called as donor impurity. Whenever there is a donor impurity, the number of free electrons will increase and number of holes, I should not say decrease, it will remain same as the intrinsic semiconductor, decrease in comparison to electrons obviously. So here the Ne is more than Nh. So what happens? The free electrons are the majority charge carriers and the holes are the minority charge carriers. In extrinsic semiconductor, both in N-type and P-type, we have something called as majority charge carriers and minority charge carriers, purely based upon the concentration of electrons and holes. We can see very clearly in the case of pentavalent impurities, concentration of electrons is more than holes. So their electrons will be treated as majority charge carriers, and in the case of N-type, holes will be taken as minority charge carriers because holes are less, electrons are more. I hope it is clear to you. So Ne is much more than Nh, that is what I told you in the previous time also. Next is P-type. What is P-type? Addition of what impurity? Trivalent impurity, because trivalent impurity will create a cavity to attract the electrons towards itself. So when silicon or germanium is doped with trivalent impurity is like gallium, indium, boron and all these things. So what will happen you see? So I am going to add a indium, or you can add boron also, whatever you want to add. So you can see in diagram you will understand that indium has 3 valence electron, these 3 valence electron is going to form covalent bond with nearby silicon or nearby germanium in this case. But this germanium's electron has nothing to bind. Here there is a cavity, isn't it? This cavity only is going to be attracting some nearby electron towards itself. Same thing, if I draw a diagram, it will be realized. So, one cavity produced, this cavity, and there is electron. Now, this cavity, what it will do? It will attract some nearby electrons. So, an electron will break and it will go to this place. And so, there will be a hole produced. And once again I am saying, since there is a cavity produced, just because of putting an indium here, the whole concentration will become more than the electron concentration, because each indium will have one less electron. If I am adding 1 lakh indium, I am going to have 1 lakh extra holes, and these holes, which are the positive cavity, is going to create some conductivity. Why? Because this 1 lakh holes will attract 1 lakh electrons. So, how the electrons will come towards it? It will break bond from the nearby germanium atom and get attracted. Are you getting my point? What is going to happen? So, there is energy level called as acceptor energy level here. But see, there is a difference between electron and hole. Electron are largely conducting, holes are less conducting. So, the hole, that is the acceptor energy level, will be near to valence band. See, I am going to draw here. See, if you remember, in the case of n-type semiconductor, we had a donor energy level, and donor energy level was near to whom? Conduction band. How much near? 0.045 electron volt. Whereas, there is an energy level in p-type semiconductor which is going to be near to valence band. How much near? They have not mentioned here the number, it is very, very less. If you see the book, you will realize the value will be given. NCERT book, any value is given? I think it is almost 0.01 around. They would have mentioned there 0.01, yes. It is like 0.01 electron volt. That is the value of energy gap between what and what? Valence band, and they have mentioned here as this gap value, no, is 0.01 electron volt as mentioned in the book. This level is called as acceptor energy level. So, if you see in acceptor energy level, there will be holes, and these holes will attract electron towards itself, and then this electron can easily go, not easily, but it can go little easier compared to these electrons. I will repeat again, why the name acceptor energy level came? Because all the holes present in this acceptor energy level will attract whom? Electron present in the valence band, and then the energy required to overcome the energy gap will be lesser compared to these electrons. They will once again jump from here to where? Conduction band. You can see and understand, and very clearly it is understandable that the conduction of p-type semiconductor will be lesser compared to n-type semiconductor. Can you feel it? Because in n-type semiconductor we have electrons, and electrons are present near the conduction level, but here we have holes which is present near the valence band. It just enhances the conductivity by making the electron to come in this level and jump little bit easily compared to the previous scenario, but not as good as n-type semiconductor, where a donor energy level comprises of electrons itself, which will definitely participate in the conduction of electricity. Are you getting my point? So, if I tell you which is more superior, obviously n-type more superior compared to p-type semiconductor. So, you can see what happened here. Okay. So, as I said to you, in the case of p-type semiconductor, who will be majority? Holes are majority charge carriers. Who are minority charge carriers? Electrons are minority charge carriers. Important. So, here NH will be much more than Ne, because every addition of boron or indium will give rise to one hole cavity. So, every hole is produced by every indium. If I am adding 1 lakh of indium atom, 1 lakh of positive cavity will be created, isn't it? So, NH is much more than Ne in this case. NH is much more than Ne in this case. You know, what word you are there? coming back. So, one thing important again for the examination point of view, that is the relationship between Ne, NH and